for the introduction, and I will be very happy to share my knowledge with all the research student, whatever I have learned during my PhD and my research work. So students, rather I will call you my colleagues because all of you are the working somewhere. Might be some of them are teachers and good researchers also. So good afternoon, everybody. Now today we are going a small discussion on a very unique characterization technique, very unique, which is really helpful in the heterogeneous catalysis. Most of you might be working in the field of material science or material chemistry, and majority of you have been doing the synthesis of the various supports. Then some of you have already characterized them and coming to a very good conclusions. Okay. But this technique is a very simple technique actually, but unfortunately this facility is not available easily in the Pune, basically. When I was working in the NCL, this is happened to be the most effective and the most used technique in the all catalytic laboratories or in the all heterogeneous fields or in the all material chemistry fields. And many of the scientists were working on this, and I get this opportunity to learn this. So I'm just giving you some glimpses so that you can learn about this technique in details in further. Also, you are most welcome to discuss with me very what you can say very formal discussion. Also, you can contact me at any time if you have some doubts regarding this, and you are most welcome for any sort of discussion regarding this topic. So we will just have a start with this session. Now, everybody is seeing the slides clearly?
Yes, sir. Yes, sir.
Yes, and I am audible very clearly to everyone.
Yes, sir.
Yes. Thank you very much. The content of my topic or content of my lecture today will be introduction, the various supports which we came across during the PhD work. Then we will discuss about the catalyst preparations. Then we will discuss about a little bit about the catalyst characterizations. And then I will focus very clearly on the pyridine characterization, which is very important. I'm just going to give a very small idea, 4 points, but I will mainly focus on the pyridine IR characterization. And then I will going to you the application of this technique, which is the most important part, and how it leads to the very good research or very good characterization of our material, which included in a very good papers, so that you can have a very good content for your manuscript or for your paper. Okay, so this is about the theme or the outline of the today's lecture. Generally, actually, why we are doing the catalysis? Basically, everybody is doing now the catalyst. Then everybody is using the terminology green chemistry, then sustainable chemistry, then affordable chemistry, then environmental friendly. So everything is condensed into a small topics like biomass conversion. So this is a hot topic in nowadays. Biomass conversion is related to directly from the biomass converted into some value-added chemicals or value-added fuels. So this biomass conversion. So from this biomass conversion, you can get the value-added chemicals, or you can have the value-added chemical synthesis, which is used, which is the most widely used during the heterogeneous catalysis is the main criteria or the main field which is used for this value-added chemicals like HMF, hydroxymethyl furan, then dimethoxy, dicarboxylic furan. These are the words nowadays which are very highly named and highly taken into the research field. Environmental sustainability, the word is everybody is knowing, but main focus I would like to say that this catalysis is mainly used for the CO2 fixation, which is the global environmental issue in nowadays. This is about the huge or brief idea about the catalysis. But if we see from the point of view of analytical chemists, from the point of view of organic chemists, so we are using the catalysis for various reactions like condensation, addition, rearrangement, coupling, multi-component synthesis, substitutions, reactions, alkylation, acylation, protection, deprotection, and polymerization. So you are using nowadays catalysis in every field. So what we are doing, actually, we are synthesizing the material, we are characterizing it, and we are applying it in the various organic transformations, or in the biomass conversion, or in the value-added chemicals preparation, or in the value-added fuels, actually. So, or CO2 fixation. So these is the main terms which are used in the catalysis field, actually. So now the catalyst is actually contains two main parts. That is a very simple or very brief idea that a support is a very different term, support, and the other one is the active species. So we will have the two different terminologies, active species and the support. Support itself can act as a catalyst. That is also one of the beautiful part of the heterogeneous catalyst. But what we will see that a support synthesis is a one major aspect or one major content of the heterogeneous catalysis, and the active species which we are going to use for the different applications is the different aspect of the heterogeneous catalysis. So now the point is, Lewis acids, solid acids, and triplets are the generally used active species for the different heterogeneous catalyst preparation. So simple, Lewis acids, like everybody is knowing, everybody had touched this Lewis acids, or every chemist is known with these Lewis acids: aluminum chloride, ferric chloride, ruthenium chloride, indium chloride, indium bromide, and so on actually. So triplets are very sophisticated things, you can say, very difficult to handle also, but not so difficult. You can use triplets like silver, copper, lanthanum. The triplets can also act as active species. And the main important part, that is the support actually, that is silica, MCM41, SBA15, zeolites, zirconium, etc. The one of the structure which I have shown on the right corner of the slide is the polyoxometallites actually. So these polyoxometallites are the very good solid acids, I can say, solid acids. These solid acids can do the fantastic conversion, and with a very little amount. Only the point is that these solid acids has to be selected properly at your support or for your support, so that these solid acids can do the miracles in the reactions or the fantastic reactions. So one of the best example is heteropolyacids. One of the best example of this polyoxometallists are the heteropolyacids, and into that it's a one class, heteropolyacids. Into that class there is a one very well studied Kegin structure. It's a Kegin structure, Del-Dawson structure, Dawson structure. So Kegin structure is very well studied, and that compound is phosphotungustic acid actually. So phosphotungustic acid is a very good solid acid which is widely used in the catalysis right nowadays, and it is a Bronsted acid. That is what I want to emphasize very, and its acidity is more than the chlorosulfonic acid. You can imagine the what type of acidity this material is having. Actually, it is more than the chlorosulfonic acid, which is acting as a solid acid, and it is very easy to handle. You cannot handle the sulfuric acid, you cannot handle the chlorosulfonic acid so easily as you are handling the phosphotungustic acid in like a FYBSc student can handle the simple solid chemicals. Okay, so these acids are very important, and these Bronsted acids having a very huge molecular weight or the molecular mass, you can say. So this huge molecular mass, just if you see the phosphotungustic acid itself is having a molecular weight about 2,880 grams. So just imagine the weight of this solid acid or phosphotungustic acid, that H3PW12O40 is the molecular formula for this. H3PW12, that is tungsten, is the 12 tungsten atoms are there, 12, and oxygen, 40 oxygens are designed in such a way that the central phosphate atom is joined by the 12 tungstate atoms. So again, very beautiful chemistry. The best Japanese scientist has first revealed this chemistry of this phosphotungustic acid actually, and this phosphotungustic acid acts as a beautiful active species for the catalysts preparation, and this active species is the mainly Bronsted acid. And I have done a fantastic reactions with these Bronsted acids in my PhD time, and this you can see them very easily on the different research websites also. Now, if you go for this, so main ingredient is the active species and support for the catalyst, and with this combination, you can design the different catalysts. Now, support plays a very important role in the catalyst or heterogeneous catalyst. Everybody knows actually. So we will just focus on the supports, that what are the supports actually. So supports are basically designed with a very good pore size. So pore size distribution is microporous, mesoporous, and macroporous actually. So microporous supports, mesoporous supports, and macroporous supports. So if you see the variety of the supports which you can have, that microporous supports like zeolites or the pillared clays, that is the bentonite clays actually. Of course, the bentonite clays are not that strong to do the fantastic chemistry, but bentonite clays can also act as a support. Zeolite, everybody knows that zeolite material is the material hugely and widely used in the petroleum industry for the cracking purpose, that is hydrocracking, for the straight line formation of the petroleum ethers actually. So microporous material. Mesoporous material is the area where all the researchers are playing a very good game actually. So mesoporous material, so you have the opportunity to synthesize a material between the size from 2 nanometer to 50 nanometer, 2 to 50 nanometer. So you have a wide scope actually. So once you have the material, you can tune its porosity by different variations, by doing the solvothermal synthesis, hydrothermal synthesis, a gel formation, and fantastic methods are also available for this synthesis. One of the best point I would like to here emphasize is that many of the researchers at college level are to prepare these materials in the lab, but I am very confident and I am very surely can assure you that you can prepare these materials in the laboratory, because we are preparing the ZSM5, that is zeolite, MCM41, MCM48, SBA15 in our own lab at college. We don't need a very sophisticated instrumentation or the very different type of apparatus or the you can say the arrangements for the material. No, definitely not. You can prepare, you can tune the material in the laboratory, or you can prepare the material in your own laboratory. I would like to suggest someone to put your mic off. I don't know who is there, but please turn off your mic. I don't know who is, what is the name actually. Please turn your Mr. Son Dotre. Yeah, thank you, thank you. So the point here is we can prepare these materials in our own lab actually. So you don't have the fear by looking at the names. You might be having the fear in your mind that whether I am in a position to prepare these materials in the laboratory. Yes, you can prepare these materials in the laboratory. And these materials are very, very easy to prepare. But the only point is it takes a time. One week you will require for this synthesis. So you can run consecutive batches. You can use the different batches so that you will have a good material in the laboratory in your hands. If you look at these structures very carefully, you will find that some of them are having a beautiful structures like spherical, hexagonal, then cage-like structure. Then the main important and very, very applicative part of is that it is having the very high, huge surface area, huge. So you will not believe that you can prepare the material with the surface area about 1400 meters square per gram. 1400, that is 1400 meters square per gram area. That is the surface area of the material. So that material, if you have in your hand actually as a support, which is having a very good properties, which is having itself, it acts as a catalyst, then you can do a number of reactions in a very beautiful fashion actually. So what are the properties of the support? Why we are doing this support preparation and this structure, its morphology, we are tuning it actually. So its textural properties we are tuning, its microscopic properties we are tuning. By the preparation of these supports or with the properties of these supports, like these supports have a very high surface area. As I have mentioned earlier, that these are having a very high surface area. That is about 1200 meter square per gram to 1400 meter square per gram. These materials have a very high dispersion ability. Dispersion ability means what? Your active species is very uniformly distributed on the support actually. So this is having a very high dispersion ability. These materials or these supports itself have actually the Bronsted acidity as well as the Lewis acidity. So these supports itself are having a Bronsted and Lewis acidity, but of course that acidity may be less, but they have that acidity as a Lewis acidity. Why to use support? It increase the catalyst life. The catalyst life is increased by taking the different supports. You have the tuning of the morphology, like see the hexagonal pore structure, the perfect structure you can your synthesis actually. It the pore size, its pore size is from, you can tune from 2 nanometer to 50 nanometer, 2 to 50 nanometers. It is having a very high thermal stability. These are stable up to 500, more than 500 degrees centigrade. These materials are stable. So they can be recycled so many times. They can be reused up to 10 recycles. We have already used this material in the lab up to 10 recycles or 10 cycles actually. They are having the very good TOF and TON. These are the turnover frequency and turnover number of the catalyst. You have to go into the deep of this when you study it individually. That is the TOF and TON, because TOF and TON are the two characteristic values which gives the importance to your catalyst. Excuse me. So now these are the various supports actually. So silica you have in your lab actually. So you can use the silica. Alumina is also you have in your laboratory. Some basic alumina is also available. Acidic alumina is also available. Neutral alumina is also. Activated carbon. Carbon can be also used as a support actually. Graphites. Montmorillonite clay, that is MMT. These are the China clay. Some people are calling it as a China clay. That can be also used as a, because why I'm telling silica, alumina, activated carbon, graphite, up to activated carbon, you have a very limited surface area. But once you go for graphite, MMT, bentonite clay, and MCM41, you have a huge surface area. So Montmorillonite is having a layered structure, layer. So between the two layer, intercalation of your active species is possible. Intercalation. And your material can go into the two layers and you have the fantastic sandwich type of catalyst during the Montmorillonite clay and the active species in the catalyst preparation. Bentonite clay is also one of the best support which is used. And MCM41, that is the mobile composition of matter. This mobile composition of matter is a company, and 41 is the code that they have. They are succeeded in the preparation of the hexagonal porous structure, that is the mesoporous structure, in the 41th batch. So they run 41 batches for the synthesis of the material, and at the 41 batch they are successful, and that's why they are calling it as a MCM 41, that is mobile composition of matter 41. So these are some supports which are in front of you. Some of the properties, that high surface area, high dispersion ability, acidity, catalyst life, tuned textural and microscopic properties of the support are also possible. Thermal stability, recyclability, reusability, TOF and TON. So that's the reason why we are preparing the supports actually, or why we are using the supports actually. Next, these are the basic elements which are used in the synthesis of support, like alumina, titania, silica, zinc oxide, and ceria actually. So I have just given the representative, or which are the used oxides. Rather, these are the oxides which are used in the form of support of various material. Now, how do we are preparing the catalyst actually? So simple preparation. We have prepared the support. We know the active species. So one of the method for the preparation of catalyst, supported Bronsted acid catalysts, supported Lewis acid catalysts. So we are using heteropolyacid, that is phosphotungustic acid, and the support MCM41. So I have prepared these catalysts with wet impregnation method, which are already reported in the New Journal of Chemistry. You can search the papers. H3 in 2017 actually. So H3PW12040 MCM41, you can prepare 10%, 20%, 30%, different combinations of PWA with MCM41. So calculated quantity of PWA. Suppose I want to prepare a 1 gram of catalyst, 1 gram, and I want to prepare a 10% of the PWA. What I will do, I will take 100 milligram of phosphotungustic acid and I will put 900 milligram of MCM41 in a solvent. Actually, in a solvent, you can have the different solvent also as per your requirement, methanol, water, and stir it for continuously for about 8 to 12 hours. Evaporate the solvent, dry the catalyst at 300 up to 300 degrees centigrade, and use this catalyst for the various applications or your research work. This is the supported Lewis acid catalyst. This catalyst also we have prepared in our laboratory and also in my research work. FeCl3 MCM41. MCM41 is also prepared in our own laboratory. That also I would like to emphasize, because the cost of MCM41 in the Aldrich, if you see, for 1 gram, you will have to pay 25,000 rupees actually, which is not possible for every researcher, or which is not possible for every guide to provide this chemical. So I will suggest you to prepare this material in the laboratory. So MCM41 we have prepared. FeCl3 is easily available. The cost of FeCl3 is also very low. Only thing is that here we have used anhydrous ferric chloride, anhydrous. So again, the calculated quantities of the active species and calculated quantities of the support mixed together for 8 to 12 hours in the methanol and dried at about 100 to 200 to 300 degrees centigrade as per your requirements actually. That's again I'm telling you. Again, another here point is this method I have shown is called as wet impregnation method. This is called as wet impregnation method. So this method looks very easy, but to prepare the MCM41 and the catalyst, it takes about a week for the complete procedure, because support is not only mixing the catalyst, because suppose support preparation involves hydrothermal synthesis, then washing it requires, then drying it requires, and then final template removal, that is called as the calcination is also there. And the calcination is done at 500 to 600 degrees centigrade for about 24 hours actually. So these are the methods for the preparation of this catalyst. So supported acid catalyst and supported Lewis acid catalyst we have prepared in the laboratory, and I had given you the a glimpse, or you can say a representative method for the preparation of the catalyst. This is one method. One of the other method is that this is, you can put the Lewis acid or Bronsted acid during the synthesis of the support also. These methods are in front of you after the preparation of support, but you can check the research papers where you can put directly the Bronsted acid or Lewis acid during the preparation of support itself, so that there is the very least possibility of leaching of the material. The least possibility of leaching of the material. So this is one of the preparation of the catalyst. So we have seen the properties of the support, preparation of the catalyst, the various supports and the active species also for our preparation of catalyst. Now, once you have been prepared with once you are ready with the catalyst, now the main task come actually. That is the main theme of our lecture, that our main idea which I want to put in front of you, that is the characterization techniques. Characterization techniques. During the characterization techniques, we can have the small angle XRD, we can do the wide angle XRD, then we have Pyridine IR studies, then we have solid state NMR, BET surface area analyzer, XPS, X-ray photoelectron spectroscopy, SEM analysis, and TEM analysis. So these are categorized into textural characterization and microscopic characterization. So low angle and wide angle XRD gives you, that is the only technique which is used for the identification of the prepared material of MCM41. That is the low angle XRD. It shows a very characteristic peak at 2.2 theta. So that is a very characteristic characterization of mesoporous material which is done by low angle XRD. Wide angle XRD, everybody knows, everybody has used it also. You have already discussed the X-ray diffraction technique. The main area which I am going to focus is the Pyridine IR studies, actually, that we will see in the next few slides. solid state NMR, you have in your mind that is it really the case that I can do the NMR? Yes, you can do the NMR spectroscopy of your catalyst as and when required. That is very important, because if your catalyst need that study, you can have the analysis done by solid state NMR. That is, if your material is having a phosphorus, because we are discussing the example of phosphotungusic acid, it involves the phosphorus, and therefore I have given the one of the more technique, that is 31P solid state NMR, which generally we are not doing it, or we are hesitating to do that, but you can have a very solid proof by doing this 31P solid state NMR analysis. I have already done and reported in the New Journal of Chemistry in my research work. BET surface area analyzer gives you the idea about the surface area of the material. A fantastic technique which gives you the idea of pore size, pore volume, diameter, then radius of the pore, then surface area of the pore, the whole in and out geometry. The whole in and out geometry of the support is done by this analysis. So surface area is done by the adsorption of liquid nitrogen and desorption of the liquid nitrogen. Then pore size, pore volume is also done by the adsorption of the ammonia and liquid nitrogen in the analysis. So you can have the fantastic idea about the area, pore size, pore volume, and the diameter actually. So why anybody will answer your ideas, or explore your ideas, why we are doing this analysis? Any guesses or any inputs you want to give to me? Yeah, any idea why we are doing this BET surface area analyzer, that we are finding out its radius, we are finding out its diameter, then pore volume? Why we are doing it?
To know surface area?
Yeah, surface area, we are doing it actually because we want to do the surface area will give us the idea that what is the surface area of the material, and it will have the very good dispersion. But why we need that pore size analysis and pore volume and diameter?
Sir, hello sir. More the surface area, it will provide more reactive site.
Sandeep, I am hearing you very little. Can you please speak loudly?
More the surface area, it will provide more active site and it will increase the reaction rate.
You are absolutely right, Sandeep. You are absolutely. But I am talking about pore size, pore volume, and diameter.
Selectivity in bonding.
Snehal, I'm listening you carefully, but your voice is too low.
You get selectivity in bonding.
Okay, we will come to that point in a little bit time. But okay, next, somebody want to talk about this? Yes, just guess it. It is a very simple chemistry, and anybody can answer it. Yes, or should I call the names actually? Okay. Okay, so we will come to the point once again. Okay. Just imagine that you have a material with you whose size is about 2.5 nanometer, whose radius or whose diameter of the material is about 2 to 3 nanometers. Diameter I'm talking. And now imagine your surface, your material or your support is also having a pore size about 2 to 3 nanometer. Then what is going to happen? Your material can insert it very easily. Your material can sit very firmly, very firmly. It can go into that pores and get fit inside that surface or inside that support, so that there is, during the reaction, there is no possibility, there is no chance that your active species is getting leached out. Leached out means it is getting out of that support. Otherwise, what will happen during the catalysis? Majority times, what happens? Active species get separated and the support gets separated. So then that is not the heterogeneous catalysis. Remember one thing: heterogeneous catalysis. Otherwise, what will happen if the active species and supports get separated? It is a simple homogeneous catalysis. You don't need to prepare the support. So you have to be very thoughtful in your mind that, are you really doing the heterogeneous catalysis, and are you really preparing the support for the heterogeneous catalysis, or are you selecting the active species very accurately so that it can fit in your pore size? That's why that pore volume is required, pore size is required. All calculations has to be done thoroughly before going for the preparation of the support or before going for the preparation of the catalyst, actually. So this, if you see, there is always some sort of attraction, some sort of bonding between the surface and active species. Sometimes there is an actual chemical bond formation happening during the support and the active species. Sometimes, but majority times, what happens, and there is a very critical review always on the research paper. They are always claiming that when you are preparing the catalyst, they always see that your material is perfectly sticked, perfectly attached, perfectly incorporated, perfectly in your support. So there is a always very huge check on this catalyst preparation. So you have to keep in your mind that active species, support, all should be in a very synchronization, actually. Otherwise your catalyst will not act as a heterogeneous catalyst. It is the homogeneous catalyst. Your active species is different and your support is different. So you are just doing the homogeneous catalysis reaction, and it's not a catalyst. I will rather say, if I am going to review your paper, I will straightforward reject it, actually. I will, if you are not very keen about your catalyst, then I will straightforward reject it, and I will say that this is not the heterogeneous catalysis, so it is rejected, actually. So you have to be very carefully calculated already the sites, active species site, support site, and your active species should get firmly attached or firmly placed inside the pores of the support. So that calculation, that idea, that survey, that literature survey, you have to done already before starting the preparation of any support. So majority times we fail afterwards, because we come to know after the preparation of the catalyst that our material which we have prepared is not meeting the requirement what I want, actually, because you have not done the prior research, because you have not done the prior literature survey. So that is the another very difficult thing, actually. So this is the idea what I want to see, actually. And now these are the textural characterizations which are done, actually, or these are the textural characterizations are dealt with. I will tell you very clearly that these are the surface characterizations. Surface, remember all this. These are the surface characterizations. XRD, wide angle, low angle, Pyridine IR, NMR, surface analyzer, XPS, all are a textural texture. These are done about the active species which is present on the surface. Microscopic characterization, like same 10, I have not mentioned the ZAPs, the ZENs, are also the one of the characteristics for the heterogeneous catalysis, actually. So you have to keep in this mind that we are dealing with the structural chemistry or the structural characterization of the catalyst. So We are going to mainly focus on the pyridine IR studies actually. So now if I want to have some sort of you can say the conclusion of the talk which I have done right now up till now actually. So what is the talk I have done? That we have prepared the support, we have the active species, either solid Lewis acids, either bronzed acids. We have the catalyst preparation method by using the active species and the support and the different characterization techniques. I am not going to talk about the infrared spectroscopy because that is going to be covered in your topic. I have just put a few slides that this is the. I am going to talk about this technique actually. This is the instrument which is used, that is FTIR, for the analysis. Actually, this IR spectroscopy is governed by the Hooke's law and everything everybody knows. This is the spectra looks like. We are going to see in details other. Now I am going to talk the main thing about the types of acidity present in the catalyst. Actually. The acidity. Why our material is acidic? Now suppose I am having a silica. So tell me that whether my material is acidic or not. Silica is acidic or basic? Anybody will tell me? Anyone? Just have a little thought, just have a little stress, and just tell me whether silica will be acidic in nature or not. Yes? Nobody wants to speak, or
Silicon dioxide is acidic in nature, sir.
I am not listening your voice, Pune. Please speak loudly.
Sir, silica is acidic in nature.
Exactly. It is simple. Silica is having a Lewis acidity, basically. Lewis acidity. It is a Lewis acidic support, actually, because it's a silica. It's a Si, and Si is a Lewis acid. That's a simple thing, actually. Everybody is knowing. Okay, then what is about the simple thing, that is the bronzed acidity and Lewis acidity? And this concept we are going to use in the catalyst or in the support analysis. So if you see now, bronzed acids like H2SO4, H3PO4, HCl, chlorosulfonic acid, heteropolyacid like phosphotungustic acid, Lewis acids like aluminum chloride, FeCl3, SnCl2, SnCl4, ruthenium chloride, indium chloride, variety of niobium chloride. Niobium pentachloride is one of the best acid which is going to be explored yet in the chemistry actually. So this is the pyridine IR instrumentation. Basically now I just have the first one more slide. Okay, this. Okay. Now, if you look at this slide very carefully, you will see some reaction. This is the pyridine we have taken because our name, this instrumentation is pyridine IR. So it is pyridine infrared spectroscopy. So taken, and suppose if we add bronzed acid, it will be the formation pyridinium ion. Pyridinium ion, that is NH. And if it is a Lewis acid, if we add pyridinium, the Lewis acid, what will happen? The metal which is present over there will get coordinated with the pyridine. Now see what we are saying, that whenever our catalyst is having a bronzed acidity, we have to prove it. It is not the only case that you say that my catalyst is bronzed acid and my catalyst is Lewis acid. No. You have to prove, you have to give the proof, because research is only based on the proof, and you have to give the evidence, you have to give the solid experimentation part. So when you are claiming that your catalyst is an acidic in nature, either Bronsted or Lewis, you have to talk about the evidence, you have to talk about the proof of the characterization, and that is the only characterization. Only, I'm telling once again the word, Pyridine IR studies is the only characterization available which is distinguishing the Bronsted acidity and the Lewis acidity. Up till now, there is no other technique which is giving you the idea that a Bronsted and a Lewis acid characterization. Pyridine IR is the only study. So this is the basic principle. What is the principle? Pyridine, when it comes in contact with Bronsted acid, it forms the pyridinium ion. And that's what we want, actually. This is what we are expecting, pyridinium ion. So, and the another one is pyridine. When it comes in contact with Lewis acid, it gets a NM bond, that is nitrogen to metal bond. See, it is a qualitative analysis. Basically, it's a qualitative analysis. It's not quantitative. But I would like to add at the end of the discussion that it's not only qualitative, it can be the quantitative. We are the second who have reported the quantitative analysis by using the Pyridine IR studies. One of the professor from AQ Venugopal, AK Akila Venugopal from IIT Madras had quantitatively analyzed Pyridine IR, and now we have already claimed our results in the coming publication. In a few days, we will see that the quantification of the Pyridine IR is done by our group in our laboratory, that we are the second who can quantify the Pyridine IR studies also. So this is a very interesting techniques. Up till now, it was discussed only about the qualitative analysis which can distinguish the Bronsted acidity and Lewis acidity, but no, there is no other technique available for this analysis. Only Pyridine IR is giving you the idea that whether your material is Bronsted acidic or Lewis acidic. It gives a very distinct separation, very distinct bands in the IR spectra, very distinct frequencies are observed, very distinct, about the Bronsted acidity and Lewis acidity. And you can have the quantitative analysis that I will discuss in the later case, actually. Spectral band positions in the IR spectrum. This is the person who had firstly discovered or who had discussed the characterization technique, that is E.P. Parry. It's a journal of catalysis. He is the person from the Madras, again IIT Madras. He is another person from the IIT, one of the IITs from India, who had given the first paper in 1963 of Journal of Catalysis. And if you see carefully, there is a hydrogen bonded pyridine, coordinately bonded pyridine, and pyridinium ion, actually. So when you see the pyridinium ion, just relate the first side. I will just go back once again. See, this is which is formed, that is NH. So this pyridinium ion will be seen in the IR spectra at about 1540 strong. A very characteristic, actually. A very characteristic peak of pyridinium ion, which is not found in hydrogen bonded also and in coordinated bonded also. But it is observed in only the pyridinium ion, that is 1540. A strong band is observed, and which gives the idea that your material is Bronsted acidic in nature. Because Diurnal is Bronsted acidic. That means that material donates H plus ion to the pyridine and it gets converted into the pyridinium ion. And that pyridinium ion is reflected in the IR spectra. And that is called as the Bronsted acidic material. So this E.P. Parry paper is firstly reported in 1963. So there are the different categories they have given: hydrogen bonded pyridine, coordinately bonded pyridine, and pyridinium ion. Actually, the one of the characteristic frequency is 1540 is the characteristic frequency for the pyridinium ion. So it is ranging from 1540 to 1545 also sometime 1545, and it is very well reported in the various literature papers. Actually, various literature papers. You can just go through, just put on the Google that pyridine IR studies, and you will have the fantastic research papers coming out with the pyridine IR studies. And these are very widely seen, a unique technique, only technique, a differentiating technique between the Bronsted and Lewis acidic character. So before going to the actual examples or applications or in the next discussion, I would like to know that you have cleared with this point or you have a doubt. So you can clarify your doubt if you are not comfortable with this. So I hope everybody is comfortable with this. Should we go ahead?
Yes, sir.
Yes, sir.
Thank you. Thank you. So we are going ahead with this discussion. Okay. Now see, this is one of the best technique which we have done. Sorry, so we will go for the first this paper. Okay. Where it is seen clearly, it is very clearly seen that this was the paper which our group has published in NGC, New Journal of Chemistry. So now we have taken the MCM 41, simple MCM 41. So just look at that MCM 41. So we have prepared the MCM 41, and if you see carefully, it shows only Lewis acidity 1450 and 1590. See, now if you go here, 1450, 1447 to 1460, and 1590, that 151590, 1600, and 1663. So if you go down, if you see, the MCM 41 is only showing the Lewis acidity. Now I have reported the spectra in 20% phosphotungustic acid when 20% phosphotungustic acid is loaded on MCM 41. So what is the logic behind it? Now see, this MCM 41 material is having in between that pores, I have shown the HPA, that is phosphotungustic acid or heteropolyacid, you can see. So this HPA is already sitting in the MCM 41. Also, it is inside the MCM 41 also. And I have used this for the deprotection purpose. That is, ethers are deprotected to phenols. That is the reaction which we have done. But we have prepared the catalyst by using the heteropolyacid. And we have characterized this catalyst by pyridine IR, where if you take only PWA, because PWA is a strong Bronsted acid, it shows, if you see, 1540 is the characteristic for NH, that is pyridinium ion formation. So that pyridinium ion formation is seen in only PWA. So only PWA shows the pyridinium ion. MCM 41 does not show the pyridinium ion formation because MCM 41 is not a Bronsted acidic in nature. But when phosphotungustic acid is loaded, when phosphotungustic acid is loaded on MCM 41, it becomes a Lewis acidic Bronsted acid. So now if you see, you have the of peaks The peaks of PWA also seen and the peaks of MCM41 also seen. Now 1540, the peak is observed. The peak is observed for Bronsted acidic peak. Bronsted acidic peak is observed for our prepared catalyst, 20% phosphotungstic acid on MCM41. So that peak is retained, or that Bronsted acidity is retained. What I can conclude from my catalyst preparation, that I have retained the Bronsted acidity, I have retained the Lewis acidity, I have maintained my catalyst to the moderate Bronsted acidity, and that I have proved it, that my catalyst is having a Lewis acidity also, and my catalyst is also having the Bronsted acidity also. So you are claiming, instead of doing the homogeneous catalyst, instead of doing the only using the phosphotungstic acid, you can use the active species as phosphotungstic acid on the support MCM41, which will give you a 20% of phosphotungstic acid supported on MCM41. Now the beautiful part here I would like to share is that, beautiful part, 20% loading. See, 20% loading means if you are taking 100 milligram of the catalyst, 80 gram catalyst, 80 gram is the support, and 20 milligram is only your active species. 20 milligram. If you are reducing it to 10%, now just see how low we can go. You can use only 10% catalyst. That means you are using only 10 milligram of active species for phosphotungstic acid for 100 milligram of catalyst. If you are going lower to that, 5% catalyst if you take, you will use only 5 milligram catalyst, 5 milligram active species for 100 milligram of catalyst. So now see, if you are going down, you are scaling down from 20%, 10%, 5%, you are achieving a very good heterogeneous catalytic study, that you are using a minimum compound, minimum amount of your active species. So that's what is expected, and that is what we are doing. The retaining the Bronsted acidity, even if you go for 5%, even if you go for below that, your Bronsted acidity will be retained. It will not change, because your support is a very good support for holding your active species. Your active species is firmly placed in the pores, in the cavity, or in the pore volume of the support, actually. And you can calculate its acidity also. You can calculate, and quantitatively you can say that you have the Bronsted acidity also and the Lewis acidity also. So this is the beautiful part where actually you are dealing with a minimum amount, because the cost of PWA might be very higher, in thousands rupees, but you are using 5 milligram, and that is worth doing these catalysts, actually. So this is one of the technique, and the only technique, again I am repeating it, there is no any other technique which can distinguish the Lewis acidity and the Bronsted acidity of the material. So you can prepare the material, you can prepare the catalyst, you can do the characterization, and one of the characterization is, this is the base pyridine IR, and this is I hope everybody understood what I am trying to give you the idea. Okay, so we'll go a little bit ahead, actually. So I will just go the back example. Okay, now here. Now if you see here carefully, MCM 41, 10% FeCl3 and 20% FeCl3. Now in only MCM 41, you will not seeing any Bronsted acidity, just a noise there you are seeing. But as you are going on increasing the amount of the catalyst, 10% FeCl3, 20% FeCl3, you are seeing the well, increase in the well of the band actually, or the band is going on expanding, and it is 1540 to 1.1542 centimeter inverse. This band is expanding. That means the Bronsted acidity is expanding. Also, it is having the Lewis acidity also. So Lewis acidity is also there, Bronsted acidity is also there, and the very simple preparation by support and the active species. So we have a very interesting catalyst preparation by using the Bronsted acid and the Lewis acid. And you can use the simple material in the laboratory for the preparation of these catalysts. So all these methods we have already reported in the paper, and we are not the only one who are doing it. Every person who is having a new material, they can prove their acidity in the laboratory. Now this is also one of the best paper. This is, some people are saying, sir, we are not preparing the support, but we are doping the material. Yes, of course, no doubt about it. You can dope the material and you can analyze it. This is the catalysis communication publication recently we have got, and you can see the studies that we have used the zinc oxide as a support. Zinc oxide. Now this zinc oxide is having the doped material titanium, various different dopings, 0.5, 0.075, 0.9 width on the zinc oxide, or we can change the different concentration or different proportion of titanium. You will see that the Lewis acidity is enhanced also, and you will see that Lewis acidity is retained also. And that is the idea where Pyridine is showing you that titanium is there on your surface actually. So you can have the analysis giving you the idea that zinc oxide is having the Lewis acidity, as well as the Lewis acidity is increased with the doping of titanium oxide. So this is again, the Lewis acidity is found to be increased as the doping of the titanium goes on increasing. Another example is best. This is the best material, that is polyvinyl pyrrolidone. This paper is in Chem plus Chem. So PVP PWA, that is polyvinyl pyrrolidone and phosphotungustic acid. These are the two overlaps of the Pyridine. Before going for the next discussion, I would like to add here is that, suppose you are recording the spectra on the machine, or you are recording the spectra on the instrument, then you are getting an ASCII file. You are getting an ASCII file where absorbance values are there, transmittance values are there, and your frequency is there. So you have to convert that data values into the Excel file, and that Excel values you can plot in the origin software. So this all the spectras were plotted with the help of ASCII values or ASCII files. These values we have copied from the instrument. These values are plotted into the origin software, where you can have the very fantastic bands seen. You can decorate your spectra, you can label your spectra, you can use in your own format, you can highlight the material by using different colors. So all this is done by using the origin software, or you can do it in the Excel file also. That is also possible, but origin is the best, or origin is better than the Excel software. Okay. So next, another here is that, now if you see Phosphotungstic acid and polyvinyl pyrrolidone are having a number of peaks, but our concern is what? Bronzed acidity is for 1540. PWA is shown with the black one, and PVP PWA is shown with the red one. Okay, so 1540, you will see a very clear matching, synchronizing peak with 1540 of PWA and PVP PWA actually. So you are retaining its bronzed acidity even though the PWA is getting complex or getting converted into the adduct, that is polyvinyl pyrrolidone phosphotungstic acid. So see, what is the advantage of it? PWA, you cannot use only PWA, otherwise it would have been the homogeneous catalysis. Now polyvinyl pyrrolidone and PWA are coming together to act as an adduct, or you can say we have termed it as a hybrid, a new hybrid actually. So that hybrid molecule is also having a Lewis acidity as well as it is having the bronzed acidity actually. So if you see carefully, 1540 centimeter inverse is the fantastic peak which is actually synchronizing with the original PWA and the hybrid material PVP PWA actually. Okay, so this is about the another duct. So we have seen the material with catalysts, material with doped materials, acidity with the complex or hybrid materials, that is PVP PWA. Now we will go ahead actually. This is a Mont clay actually. Okay, I will go for one more very good spectra rather than this. Yes. What you are seeing, see here also we are getting the peaks at 1545, 1450, 1610, 1490. All these peaks are for Lewis acidity and bronzed acidity. So bronzed acidity peak is 1545, bronzed acidity peak. Now if you see that this actual idea is for as you go on loading the material, that means what? 10%, 20%, and 30%. So MCM 41 is same. MCM 41 is the support, but initially it was having only 10% PWA. Then it was done with 20% PWA, and after that it was done with 30% PWA. So if you see carefully, the peak at 1545. So if you see 1545 is exactly going on increasing. Now see, it is 1550. At 10%, you are seeing just a hump, or you are seeing just a bump, which is just showing a peak here. But if you go to 20%, the peak is enhanced or the bump is increased. And at 30%, you are getting the very good intensified bump. So as you go on increasing the loading as 10%, 20%, 30%, PWA loading is increased, bronzed acidity is also increased. You can talk about the Lewis acidity also. That Lewis acidity is also going on increasing. Now see, 1450 is going also increasing. 1490 is also going on increasing. 1640 is also going on increasing, and 1590 is also going on increasing. So this conclusion you can draw that the acidity increased gradually with increasing phosphotungstic acid loading actually. Now this is also one more material, but I would like to highlight this also, one of the best papers of our group actually, that is the Chemistry Select, a recent publication from our group. So here, ionic liquid, this is one of the major class or a beautiful class of chemistry, do the wondrous reactions actually. Ionic liquids, these are the imidazole based ionic liquids with the sulfonic acid or sulfonic acid catalyzed. You can say like this. So we have prepared 4 different ionic liquids, and you see very carefully the bronzed acidity, because these are the sulfonic acids actually. So these sulfonic acids, as you are seeing that they are showing the bronzed acidity very nicely at 1546 centimeter inverse. So IL1, IL2, IL3 and IL4 actually all are showing a very good bronzed acidity, that 1546, 1546, 1546 and 1546. So this clearly indicates that you use the solid material, you use the doped material, you use the hybrid material, you use the various ionic liquids, number of materials you can use and prepare and characterize and state and conclude that these all are acidic in nature. This is the solid evidence, a best characteristic technique for the bronzed acidity. So this is the result which we have published recently in Chemistry Select 2024 actually. For now, see, we have done this for the synthesis of the fantastic monoterpene transformations which are not yet reported. Digeranyl ether, we are the first to report by the heterogeneous catalysis. Earlier, the methods have reported it by the classical organic chemistry. The geranyl phenols, these are also the one of the best achievement of our group, that we are synthesized 11 different medicinally active compounds actually. But my point is, these ionic liquids which are bronzed in nature are used for this convergence, and this bronzed acidity is mentioned, or this bronzed acidity can be characterized by using the pyridine IR technique actually. Now this is about the qualitative analysis. All we are discussing about the qualitative analysis, and quantitative also we can do, as I have mentioned earlier also. Now see, we have prepared a series of catalysts. Just see 20% indium chloride, stannous chloride, nickel chloride, niobium chloride, cobalt chloride, cadmium chloride, aluminum chloride, FeCl3, number of catalysts. And if you see very carefully, you will observe that some of them are showing the bronzed acidity and some of them are not showing the bronzed acidity. So you can choose, or you can tailor, you can modify the Lewis acidity, the bronzed acidity. You can select the catalyst on the basis of your requirement, whether you want a bronzed acidic catalyst, Lewis acid catalyst, or bronzed and Lewis acid catalyst. So you can have the fantastic idea for your selection also. That is used in the catalyst screening also. That is used in the optimization study also. You can use in a different analysis. This is the one of the best method which we have done right now, and we have reported this, which will be seen to everybody in the few days actually. This is the best method which we have reported second time after the Akila Venugopal from the IIT Madras, who has quantified the acidity. We are the second who are reporting it actually. I am not disclosing the all part, but I am just saying that this is the deconvoluted pyridine IR. So now this is a deconvolution. Deconvolution is done for the XPS analysis of the spectra, that is X-ray photoelectron spectroscopy. But now we have used that technique for the deconvolution of IR spectra, that is pyridine IR spectra, and we have quantified the details. We have calculated the area under the peak, percentage area under the peak. Then we have calculated the total Lewis acidity in percentage, and then we have calculated the total bronzed acidity in the percentage, and we have make the ratio also. That is Lewis to bronzed acid ratio also we have commented by using this catalyst. So this technique needs a very good practical hand, a good concentration, and a very clear concepts for reporting such a value characterization. So you can also do this. You have to go through all these technique, minute details of this technique, and you can do the number of analysis also. These are the plots for which we have done for FeCl3. Just see that FeCl3 is in different proportion. 1%, 5%, 10%, 20%, 30% we have loaded, and we have quantified the 1% Fe. Remember, 1% Fe is very difficult to handle. That also we have analyzed by using the deconvolution, that is the quantitative measurement of area after the peak actually. So this is about the techniques, but now I am going to talk about the actual instrumentation. So before going to the instrumentation part in details, I would like to have the queries actually. I would like to know your doubts and your questions before going for the instrumentation, because application is more interesting and more easy to learn rather than instrumentation, because instrumentation is very difficult for understanding, and many of the peoples may be not happy with that, but it is also the part and parcel of the research, so we have to focus on that. So if you have queries or doubts or some questions, you can ask without hesitation. Even if a very small question, do not hesitate, because we all are here to learn. We are researchers. Basically, I am also a student. So if I am also getting a good initiative from you, so that I can improve my own research, my own ideas I can put, and it will be helpful for the research community. That is what is expected. Yeah. So please, if you have any doubt, please ask. Yes. No doubt. No doubt. Okay, let me ask you one thing. Are you ready to do this analysis in your research or not? Or everybody left the class? Hello?
We will do it, sir.
Yes, sir.
You will do it. Okay. So let us have
Yes.
a quick refreshment, or let us have a quick break. Please turn on your all mics. I just want to see you all, so that everybody will be once again cautious and will be there in the class back in within few minutes. So please turn on your all cameras so that we will see everybody. Yeah, please turn on all your cameras so that I may be knowing you, you may be knowing me. Hi, Wasim sir. Morning.
Good evening, sir.
Good evening. Good evening. Good evening. So, oh, Yes, sir.
Yes, sir. Sorry,